One thing that makes mathematics both important and fascinating is its ability to make precise the world around us. Think about blowing a bubble. The soap and water mixture will enclose however much air we blow into it, all while clinging together as tightly as it can. Therefore, a bubble will become the shape that minimizes our surface area to volume ratio, a sphere. Within mathematics, if an object achieves a minimum for the surface area to volume ratio, just like our bubble will, then a quantity called the mean curvature of the object will be the same at every single point along the surface of that object. Imagine an ant walking on an orange. The surface of the orange curves equally as the ant walks along it if the ant walks in the forwards direction or if the ant walks in the sideways direction, no matter where our ant is. This is because the surface of a sphere at every single point curves equally in every direction. This is different than if our ant is walking on the surface of a pumpkin, where there are places that are very flat and there are sharp valleys that our ant is walking in and out of. At different points along the pumpkin, the ant's path has to curve differently as it walks along. The mean curvature of an object is the average of how much the object curves in the forwards and the sideways directions at a particular point. On our sphere, because at every single point the sphere curves equally in every direction, this number will be the same everywhere. But on our pumpkin, because there are places that are very flat and there are others that are so sharp, this average will differ from point to point. Now, there are other surfaces, such as a cylinder that goes on forever, or this bumpy cylinder called an undulate, also going on forever, that have this constant mean curvature property. The mean curvature is exactly the same no matter where we are on the surface. But the sphere is the only closed-off shape with this property. Sadly, we don't have an infinite quantity of soap and water, so when we blow a bubble, we get a sphere. Think now about oil bubbles moving around in a lava lamp. Those aren't spheres. The physical equations that govern the geometry of a bubble change when the bubble and the world around it are in motion. In particular, the portion of the equation that changes is the mean curvature. In a lava lamp, as the water moves up and down with the oil bubbles become stretched out, mirroring this motion. So, if a bubble is in motion, then the mean curvature will no longer be the same at every single point along the object. The way in which the mean curvature varies from point to point will reflect the way in which the bubble is moving. So, if we know exactly what type of motion we have, we know exactly the mean curvature equation that our bubble has to satisfy. This is the geometry that I do. I start out with an equation for the mean curvature that I want an object to satisfy, and I try and build a bubble that will have this mean curvature exactly. Now, I don't get to play with any actual bubbles other than for my own enjoyment. Mathematics is a poetry of precision, and my research is to try and build brand new shapes that meet a particular set of curvature criteria exactly. Mathematically, it is a really fascinating question to just study the geometry unto itself of what bubble shapes can possibly exist. This here is the equation for the mean curvature of a bubble in a whirlpool. 1 plus tau r squared. Tau is a small number related to how fast the whirlpool is moving, and r is the distance from where we are on our bubble to the center of the whirlpool. One of my projects is to try and build a bubble that will make a ring around the whirlpool. Instead of trying to invent a shape from scratch, if I am building my bubble super close in to the center of that whirlpool, then I can start out with shapes that I already know have mean curvature exactly equal to 1 everywhere and use them as building blocks. In particular, I start out with a collection of spheres and these connecting tubes that I get from my undulate to use as bridges. I glue the spheres and the connecting tubes together until I formed a ring. Now, this original cut and paste job won't satisfy the curvature conditions that I need. Where the tubes meet the spheres, there's a messy junction. And the spheres that I'm starting with are perfectly round. And I need them to not be, because I had that extra component of my mean curvature equation that reflected the motion of the whirlpool. But by designing my rough shape very carefully, specifically by figuring out exactly how small I need to make the connecting tubes and at what angle I need to attach them, I can then nudge or deform my surface a microscopic amount. The spheres will bulge a tiny bit differently, the tubes will flex at a slight angle, and suddenly the messy seams vanish, and our ring will satisfy the curvature criteria for a bubble in a whirlpool exactly. Mathematics is about invention with precision. Through exploring geometry, we can harness its power to make precise the world around us. Thank you.